Hello, I'm Malcolm Sherman Godfrey, a systems design engineer at Analog Devices. Today, I'll be unboxing the eval ADMX6001 kit, a DC-coupled 10 gigasample per second digitizer reference design, and walking you through the setup process to kickstart your ADMX6001 evaluation journey. With the eval ADMX6001 board, you can digitize broadband signals from DC to 5 GHz at 10 gigasamples per second, achieving low noise with exceptional measurement accuracy. The eval ADMX6001 kit includes the eval ADMX6001 board and a 12-volt power adapter. The eval ADMX6001 interfaces with the off-the-shelf Xilinx VCU118 FPGA board via the FMC connector. For a complete setup, you will also need a laptop with required software installed and an Ethernet/USB adapter, and a small desktop fan for heat dissipation. Use standoffs to reduce the strain on the FMC connector and make sure to stabilize the board. Ensure the FMC connection is secure. Now, let's power it on. Plug in the 12-volt power supply to the eval ADMX6001 board. Confirm DS10 and DS11 are lit up. After a few seconds, switch on the VCU118 FPGA board. With the hardware powered up, we're ready to program the VCU118 FPGA board. You'll need Xilinx Vivado Lab Edition for programming the VCU118, and TeraTerm or another UART terminal for communication between the VCU118 and the computer. We've pre-installed and configured all required software in advance to save time today. For detailed setup instructions, refer to the eval ADMX6001 wiki page or user guide using the links shown here. To program the VCU118 FPGA, open a command prompt and navigate to the folder with the boot files for the eval ADMX6001. Run xsdb.bat with its full path. You will see the prompt change to xsdb. Type source run.tcl to begin programming. While waiting for the FPGA programming to finish, launch your preferred terminal. Here, we're using TeraTerm. Select Serial and choose the Silicon Labs standard port from the pull-down menu, then click OK. In TeraTerm, click Setup, look for Serial port, and then set the baud rate to 115200. The terminal is now ready to send commands to and receive status messages from the VCU118 board. Let's go back to the Vivado Lab programming window. Once the programming is finished, the xsdb prompt reappears and the VCU118 booting starts, with messages appearing in the TeraTerm window. Once the boot process completes, a login prompt will appear in the TeraTerm window. Sometimes, an error occurs during the VCU118 process that prevents communication with the eval ADMX6001. To avoid this, we recommend running the boot process a second time as soon as it finishes. After the second boot, log in using username root and password analog, both all lowercase. Notice the hashtag prompt appears after successful login. To verify the Ethernet connection, type ping 192.168.2.1 in the VCU118 programming command prompt window. Now we're ready to configure and control the eval ADMX6001 board. There are two ways to interact with the board: using IAO oscilloscope for manual register access, and using Python scripts for automated control. In this video, we'll focus on the Python scripts. The PyADI IAO library can be used for configuration of the eval ADMX6001 by checking out the ADMX6001 v1 branch. My Python virtual environment is already set up with all necessary libraries. You can find instructions for setting yours up in the user guide. Open a command prompt, navigate to the Python virtual environment, and activate it. You'll see the prompt change accordingly. The 804080 in the precision path uses low voltage differential signaling, or LVDS, for data interfacing. After powering up, configure the 804080 LVDS registers 15 and 16 using the Python script ADMX6001 804080 cal.py. Next, set up the function generator for a waveform with your desired frequency and amplitude. I'm using a 2 MHz, 200 mV peak-to-peak sine wave. Make sure to enable the output. Now I'll run the data acquisition Python script. In this script, you can change the bias voltage supplied to the ADL5580 driver amplifier to move the baseline voltage up and down the ADC window for best use of the input dynamic range of the AD9213. This feature makes it easy to handle a wide range of DC voltage levels in real-world signals generated by sensors or detectors. Captured data can be saved as a CSV file for easy processing and visualization. Now I'll switch the input signal to a pulse train. With its 10 gigasample per second sampling rate, the eval ADMX6001 can capture pulses as narrow as a few hundred picoseconds. Now I'll run the data capture script again so you can observe the offset adjustments. The eval ADMX6001 offers far more capabilities than those shown here. We encourage you to explore its full potential. For information on documentation, example scripts, and more resources, visit analog.com/eval ADMX6001.